Morning everyone. So this will be our first lesson. I just wanted to start reviewing with you some of the kinematics. Hopefully you haven't forgotten all of this, but I know it's been a little while since we've seen it, so let's just go ahead and go through this. I would encourage you to have out your notebooks and just fill through details as we go through examples. I mentioned before, once we write out the question, you can just hit pause on the video, try out the question for yourself, and then resume afterwards and have a look at how you did. So this is a summary of our kinematics. So this is our first chapter. Kinematics, if you remember, this one here was the study of motion. Okay, this is where we started talking about displacement, velocity, acceleration. We introduced our kinematic formulas that are upcoming. First thing that we did in this chapter was we separated quantities of physics into the two areas. They're either scalars or vectors. Scalars are things that only have magnitude. Magnitude is just the number. So if I take, for example, 5 steps, the 5 there is the magnitude. Steps would usually be in meters for SI units, but magnitude is just that number there. Vectors also have magnitude, also have that number 5, but they also have a direction implied to it. So that's what sets apart vectors from scalars. Because vectors have a direction, you see on the right side here, we represent vectors with an arrow. The size of the arrow, or the magnitude, is represented by how long the arrow is. That's the magnitude. Whereas the direction, whichever way that this arrowhead is pointing, indicates the direction. If you remember, as long as there's no change in direction, scalars and vectors are the same. Okay, so just include that here. These two quantities are the same if there is no change in direction. And you saw in the examples that we've done previous is if there is a change in direction, we can break up the motion into multiple parts. When I'm going forward, I can study the forward part of the motion. If it reverses and goes backwards, we can study that as a separate motion individually. Let's skip down here to our 5 kinematic equations. Primarily, most situations that we're going to have will involve having acceleration. So we're looking mainly at equations 3, 4, and 5. All of these have this acceleration term in sight. Remember, these formulas here are all interchangeable. We can use the formula if we have everything known except for one that's unknown. Just a quick comparison of the different formulas themselves. This third formula here, if you remember, this came from the definition for acceleration. Acceleration was defined as the change in velocity over change in time. When we rearranged that expression, we ended up with this expression, Vf equals Vi plus At. You'll notice equations 3 and equations 5, both of them involve final velocity of some sort. So if the question is asking for you to calculate final velocity, or if you don't know it yet, you'll know to use one of these two formulas. The other way you can look at these formulas here is the 3 and 4 have to do with time. So if you're having time information, you can consider using those two. Whereas if you have some distance information or displacement, you can refer to equations 4 and 5. Equation number 1 is called the basic motion equation. The reason why it's basic motion is because basic motion implies that there is no acceleration. If there's no acceleration, if you look at equation number 4, when you set an a equals 0, that term dies away and we end up with simply displacement is the speed times time. Remember, with our blindfold analogy, you can set your initial and your final to whatever's convenient for you. Depending on the problem, you can reset initial and final. Just make sure you have a very clear list of what your variables are with the units. Remember, when we include numbers, we do want to include them with the correct sig phase and as well units as well. For these formulas here, these ones here, they do like initial and final separately. We introduced 2 types of graphs to study the in-between motion. So one of them was called the displacement time graph, also called the position time graph. This one here, as the name suggests, it shows you the position or your location as at any point of time in that interval. So we have displacement here on the y-axis. If you remember, it's like a guy here. He's standing at the starting line when a d is equal to 0. His race is going up or down. When we are above on the displacement time graph, we would have positive displacements. Remember, based on our convention, positive displacement means you are in front. Okay, not necessarily forwards, but you are in front of the line. When you are dropping below, again, this would have to be the vector for your displacements to actually go into the negatives. Remember, the negative just implies we are behind. And again, the implication there is not necessarily that we're heading backwards, but that we are just behind the starting line. Time is your independent variable. This is the one that's on your horizontal. This is just going to keep ticking on. It doesn't matter where the guy is at any point, but as the clock ticks forwards, we can track the motion. Does he end up getting farther? Does he end up speeding up, slowing down? We can study his motion as time ticks forwards. That's how you study your displacement time graph. Remember, one most important feature for the displacement time graph, we'll do a few examples later on, is that the slope. If you look at the slope here, slope is rise over run. The rise is going to be a change in displacement. The run is going to be a change in time. If you rearrange equation number 1 here, d over t, that actually gives you your velocity. The speed of this person at any point in this motion here is given by the slope on the displacement time graph. The other type of graph here that we introduced was called a velocity time graph. If I can scroll down here. For a velocity time graph here, instead of plotting the guy's whereabouts, what we're plotting here is the speed as time goes onwards. So just as previous here, time's just going to tick onwards, not caring about anything. Okay. What we have here is we have positive velocities on the top. This time, for velocity being positive as our convention does actually imply that it's forwards. So as long as your graph is in this upper y region, we know this guy here is heading forward. He may be speeding up, he may be slowing down, but at least his direction and his heading is getting further and further in the positive direction from the starting line. As the graph here drops below, when your velocities start going negative, this one here does imply he's actually going backwards. And again, he could be speeding up or slowing down. He may even be in front of the starting line, but at least his speed or his velocity is going backwards. There's two main things we can calculate from this velocity time graph. Similarly, we can calculate the slope on this graph. This time your vertical, the rise is actually given as a delta v. Your run is going to be a delta t. We just derived this earlier here. If I take a delta v over delta t, that gives us the definition for acceleration. So if you want to indicate for yourself what is the acceleration, how quickly is it speeding up, or even decelerating, remember whenever your speed and your acceleration are in opposite directions, so you tend to slow down, that would give you acceleration. Just for simplicity, for your position time graph, especially when there is an acceleration, you can end up having a curve type motion, whereas for a velocity time graph here, for physics 11 and physics 12, we're going to always assume uniform acceleration, meaning that there's no change in velocity. Or sorry, let's say that again. Uniform acceleration meaning, velocity may change, but the rate at which it changes will be a constant. So on this type of graph here, we might end up seeing horizontal lines or just diagonal lines, but no curves on the velocity time graph. Seeing as this velocity time graph here does not show you motion, what we can do here is we can actually try to figure out displacement. How far does the guy actually get? If you look at the displacement formula here in equation number 1, your displacement is given by your velocity times your time. Velocity times time, velocity is going to be your y-axis again. Time is going to be your horizontal. When you multiply those two, that's implying, in calculus we call that the integral, okay? But it's the area under the curve. Especially if this curve here drops down to the negatives here, we're going to do the area bounded by the curve. Areas on top are going to be positive. Areas on the bottom are going to be negative. Positive displacement means he heads forwards. Negative displacement means he heads backwards. So that's how we read those two graphs there. Okay, you may already have some familiar with position time graphs. Usually I find people have a little bit more trouble with the velocity time graph. As we start looking towards our kinematic equations a little bit more, we know on the Earth's surface, the acceleration due to gravity is a constant negative 9.8. The negative there just implies a downwards direction. For some problems, you might find it more convenient to define downwards as actually positive. So say, for example, if I am holding an object and I simply drop it off, I might decide to say, well, velocity is actually positive in the downwards direction. Acceleration, similarly, is also in the downward direction. Because those two help each other, we know it's going to speed up, but we can call those both positives to make it simpler than having both of them as the negative. Remember, this negative 9.8 constant is only true for the Earth, and it's only true at a distance close to the surface. In physics 12, when we get to satellite distances or plane altitudes, this acceleration here will not necessarily be 9.8, but we saw in chapter 2 how we can figure out what this constant is. Lastly, before we try out a few questions here, is we looked at two-dimensional kinematics. we saw that two-dimensional motion can be broken down into x and y components. The key part here is that the x, which is the horizontal, which is the x, and the vertical, which is the y-axis, are completely independent of each other. These are completely independent. So both motions can happen individually without regard of what's happening to the other. This is, if you remember, why we separated our columns into here's what we know about x, here's what we know about y. For most of our questions, we had an acceleration in the x direction of 0. This is not always the case. If I have a rocket and it has thrusters that can actually make me accelerate forward, speed up or slow down while I'm moving, this is not necessarily going to be 0. But for the problems that we did, say a meatball question, a football question, or a cannonball question, all of those, the instant that the car leaves the ground, the instant that the football is in the air, or the projectile gets thrown, there is no more speeding up or slowing down because we're in the air. Acceleration in the y direction, we're going to, assuming that we're on the Earth's surface, acceleration is going to be negative 9.8. And depending on how the question is worded, then later on, we can figure out the rest of the problem. So that there is just a quick overview of this chapter. What I'm hoping to do here is I'm going to hopefully just walk you through a few examples. Here's where you can just test yourself here. It's one thing for just watching how the notes are being done here, but it's good, just practice for yourself. Even if you understand it, practice it so that you can do it fairly quickly. So I'm just going to scroll past our questions here. First question here we're going to look at is an example of vector addition. So vectors, if you remember, these are things that have both magnitude and direction. So say for this question here, I want you to add the two following vectors. I have a vector that is 10 meters pointing in the eastward direction. Once I've walked the 10 meters, I'm now over here. I'm going to now walk at a diagonal. Let's walk, say, 15 meters at an angle of, let's say, 50 degrees. I wanted to show you in this question here, vectors are being added head to tail. We're doing the blindfold on, blindfold off analogy. We want to know from start to finish. If I didn't watch this person actually do this motion, I want to know how far displaced, how far pushed away is he from his starting position. If you remember, what we're going to do is we're going to take the vectors here and we're going to break down components. Horizontals we'll add together with horizontals really nicely and verticals separately. That'll end up creating for us a triangle that has as its hypotenuse the displacement that we need. The first vector we have no problem. 10 meters east is just 10 meters east. So x1 is going to be 10 meters. There's no vertical component for that first vector there, so it's 0 meters in the y direction. For x2, this one here is the second triangle here. We have our 50 degrees. I'm going to call this length here, I'm going to change color for you here. I'm going to call this length here x2, call this length here y2. Test yourself here, which one is sine and which one is cos. You have to refer to the triangle and the angle that's given. In this case here, because the 50 degrees here is this angle, we know that the x is the adjacent side. When we do SOHCAHTOA, we see that the x is going to be the adjacent. So in this case here, this would simply be 15 cos of 50, whereas the other case here, 50 sine of 50. Make sure when you do this degree stuff here that you are in degree mode, especially your graphing calculators tend to be in radian mode. So 15 cos 50. Calculator may end up spitting out a really long number. Remember, eventually we just want 2 or 3 sig figs, so I'm just going to round it to 9.64 for now. 15 sine of 50 gives me 11.5, give or take. For this stuff here, we are going to just go straight back to our conventions. Remember, for our conventions, if we're looking at a side view problem, which are not in this case, for a side view problem, our guy can go to the right or go upwards. Those directions are implied as the positive direction. If we go to the left or backwards, change color here, colors have disappeared. If we can go to the left or backwards, or we go downwards, that would imply that we're in the negative direction. For this case here, I'm imagining we're a top view problem. We're in a helicopter and we're looking down at this motion. That's why we have the direction east here. Okay. Remember, for a top view problem, we're going to have our coordinate system. We have our never eat, try to eat. Never eat is going to be the positive directions. When you have your south and your west, these are your negative directions. So when you add these vectors, we can come along and we can add negatives sort of haphazardly here, and we can actually decide which ones are positive, which ones are negative. We'll notice x1 is east, positive. x2 is also east, positive. The only one that potentially may be negative here is going to be the y2. When I am walking 50 degrees in the southward direction, I want to come along and add that negative. So this is a negative that we just implied just so that we get our directions correct. Now that we have things broken down into x and y separately, we can just figure out, well, what's the total amount of x that we did, which is simply going to be x1 plus x2. In this case here, first part of the motion took us 10, second part of the motion takes us an additional 9.64. I can do that math there, so 19.64. Let's say it's meters. We can add the y's. Not as interesting. y1 is actually 0, so I didn't go north or south from this vector here, so 0 there. We have a negative 11.5 for y2. That takes me a negative 11.5 overall. When you add those two up, if you just match up to the picture, the 19.64 actually refers to this entire distance here. So that's going in the eastward direction, 19.64. The negative here still implies that we're southwards. In this case here, the downwards direction is now at 11.5. We've now created a new triangle. If we use our Pythagoras, we can then figure out the values. So let me just sketch out that triangle and we'll finish off this problem. The total distance in the y direction is now at 19.64. We're heading downwards at 11.5. Once I have the arrowhead pointed, you'll notice that I don't necessarily need to draw this negative anymore. We're going to use our Pythagoras, and we're going to try to figure out this hypotenuse. Because displacement is a vector, we also need to apply that theta there. The theta would give you the angle of depression. So let's do our Pythagoras. The hypotenuse is given by the square root of a squared plus b squared. So 19.64 squared added to 11.5 squared. We'll do that in my calculator here. 19.64 squared plus 11.5 squared. I'll take the square root of that answer. This gives me 22.8. Overall, I am 22.8 displaced. You'll notice that that is actually more than your less than your total distance. Your total distance was, I actually walked about 20 meters, another about 11. I've walked about 30 some meters, but because there was this change in direction, we ended up only getting 22.8 pushed away from our starting point. To get the theta here, because I actually know all three sides, you're welcome to use sine, cosine, tan. Just in case I got this hypotenuse wrong, I tend to prefer like using tan at this point. Tan is SOHCAHTOA. TOA would apply to the opposite and the adjacent. So we can just do the inverse of tan to go 11.5 divided by 19.64. Again, you'll notice that I've ignored the negative here. I already pointed it in the downwards direction. If you do the inverse tan of positive 11.5, it will still give you the same answer. I'm going to type this in here. The inverse tan of 11.5 divided by 19.64. That gives me 30.4. Because we are in a top view, I know I'm heading in the southeast direction. Remember, there's a choice either to write this here as south of east or east of south. We're going to treat our second direction as the pure direction. In this case here, because the pure direction is pointed straight east, and I'm starting to aim 10 degrees, 20 degrees, 30 degrees, at 30 degrees southward, we're going to choose the south of east option. In this case, it is not going to be the east of south. Especially for multiple choice, however, when we're trying to match up our answers, it's possible I could have given you the other angle. Because these angles here are complementary, meaning they add to 90, I can also imply 90 minus this answer here. It could have also been written here, 59.6 degrees east of south. So that there is an example of a vector addition problem. That'll show up in the next chapter on momentum, so make sure you do practice that there. Next question I want to do with you here is a position time, velocity time graph sort of question. So let's take a look at a position time graph, d versus t. And we'll just try to scale it out. 1, 2, 3, 4. Make this 10 and negative 10. So I'm going to sketch a motion for you here. Let's say So he does this string for a second. He does this one here, there's a nice curve. Then he goes downwards, just like that. And then let's do another curve. So, again, what you can do at this point here is you can just pause the video. You can have a look, see if you can label what is he doing in each parts of these motions. In section A, B, C, and D. And then because this is a position time graph, I'm going to ask you, not only are we going to list what he's doing, I want you to also calculate the instantaneous velocity. Calculate the velocity at the instant, at the one time. Let's do a time of, say, 1. Assuming you pause the video and press play again here, in part A, as the clock goes onwards, you'll notice that his position doesn't change. At 0 seconds, he's at 10, a little bit later, he's still at 10, a little bit later, he's still at 10. In part A, he is completely at rest. His speed is equal to 0. In part B here, we already talked about speed being the slope on this curve here. If you use your ruler, you'll realize here at first, in the region of part B, the slant is in the negative direction and it's really, really steep. As it goes forwards, however, we'll notice that how steep this slope gets actually gets more and more shallow. So we're getting less and less steep. The magnitude is getting smaller, implying that we're slowing down. But the direction that we're heading in, this is taking us closer and closer to the starting line. So B here, direction-wise, he's heading backwards. He was in front at the first, but he's heading backwards, but we have to slow down. In part C here, he's again heading downwards. So he's going to be, a little bit later he's at -2, a little bit later he's at -4, a little bit later he's eventually gets to -10. We know direction-wise he's still heading backwards. This time, because the slant is a constant, doesn't matter early on or a little bit later, it's still a constant steepness. We have a constant negative velocity. And lastly here, you could still use that slope analogy. Is it getting more slanted, less slanted, to figure out speed up or slow down? Probably another way of doing it, just for an alternative, is you can actually do this sort of staircase model. Give yourself a certain interval of time. I go that far. In the same time, if I go this far, in the same time interval, whoa, I go that far. In the same time interval, whoa, I go that far there. Because I'm covering more and more distance as time goes onwards, I know it's speeding up. But because I have a heading going forwards, going upwards, so this one here is going to be in the forward direction and speeding up. How'd you do? Let's calculate here the instantaneous velocity. We know that the slope on a position time graph is the speed. The trouble with this one here is, if I look at a time 1.5 seconds, we are in the middle of a curve. We are in the middle of the slowing down region. It's really hard for us to find the slope at this point, let alone we only have one single point to actually calculate at. If you remember, what we did is we would take out a ruler, we would try to sketch what's called a tangent line. A tangent line is a straight line that hopefully, if I zoom in at this point here, hopefully my tangent line will follow the curvature of the curve at that point there, so that when I'm really, really zoomed in, pretty much my curve and my tangent line will be overlapping each other. Once you have your tangent line, that slope never changes, so you can pick any 2 points that are really easy for you to read on that tangent line, pick 2 points, say this point and this point there, calculate the instantaneous velocity. y2 minus y1, x2 minus x1. Here's an example of a position time graph. Let's do an example of a velocity time graph as well. Hopefully this is slowly coming back to you. Here's your velocity time graph. Let's again sketch it 2, 4, 6, 8. Be careful of your scale. The scale on the x and the y don't necessarily have to be the same. Let's start off here. Let's have it also go horizontally. Let's have it go up to a 10 in velocity. Velocity time graph, your speed can change a lot more instantaneously, so it's possible that this one here might jump into the negatives, and let's just go down this one. So similarly here, I'm going to give you 4 letters. Let's say this one here is E, section F, section G, and section H. Take a second there and see if you can figure out for yourself what is this object doing in the forward parts motion. part E, definitely we see that the slant is constant, but because this is a velocity time graph, we're saying at 0 seconds his speed is 5. A little bit later he's still going 5. A little bit later he's still going 5. He is actually traveling, so in this case here it's forwards, it's in the positive direction, but definitely the velocity is a constant. For the second time interval in part F, between 2 and 4 seconds, as time goes onwards, he goes from that 5 meters per second to maybe 7 or 9 or 10 meters per second. You notice that speed is increasing. We are still in the positive region for your velocity, so we know that we're definitely heading in the positive direction. In this case here, because the number is getting bigger, we know it's going to be speeding up. In section G, we have jumping into the negative regions. When your velocity jumps into the negatives, we know our direction is backwards. I might still be in front at this point, seeing as we've gone so far forwards, but at least direction-wise, we're now heading in the opposite direction. My speed goes from, say, a -5, a little later -3, a little later maybe -2. You'll notice the negative just indicates the direction for you, but going from the speed 5 to 3 to 2, it definitely means we're slowing down. We're slowing down in a backwards direction. Exactly the opposite in part H. We're still going backwards, we're still heading in the negative direction, but our magnitude is going -1, -3, -5. Our speed is getting bigger, the magnitude is getting bigger, the speed. For this graph here, I can ask you 2 questions. One is calculate the acceleration, calculate the displacement. So let's do acceleration first. So that's this part B of the question. Find the acceleration between 4 to 6 seconds. You know, it's different from the earlier question. I don't necessarily have to just give you a time. Seeing as the acceleration will be constant here, I could give you an interval for you to calculate over. Because we know the acceleration is the slope on this VT graph, I'm going to choose 2 points that are easy to read. Again, y2 minus y1, x2 minus x1. It doesn't have to necessarily be those 2 points here. My coordinates here are 6 and 0. This one was a 4 and a -5. If I go y2 minus y1, a 0 minus a -5, a 6 minus a 4, this gives me 5 over 2. Don't leave your answers as a fraction here. Keep your answers 2 or 3 significants with the appropriate units. The acceleration there is positive. Although my acceleration during this region here is positive, because my velocity is negative, because the speed and the acceleration are different directions, we imply that to slow down, and that confirms this assumption. Last thing we can do here for the displacement. Displacement is given by the acceleration. So let's say we want to calculate the displacement between 0 to 4 seconds. We know we want the area under the curve. This area here is going to be fairly easy. It's a base of 2 and a height of 5. So for that first part of the motion, I'm going to go 2 times 5. For the second part of the motion, although this part here does end up as a trapezoid, if you don't know the area formula for a trapezoid, you can simply break up a trapezoid into a square and a triangle. So this bottom square here, which I'm labeling in blue, again has a base of 2, has a height of 5, so let's add another 2 times 5, so it's going to be an extra 10. But in addition to that, we actually add a triangle. The area of a triangle is given by base times height divided by 2. The base again is 2, then do another 5, but this time our formula before we go 2 times 5 is going to be plus 1 half. We add up all those numbers there, we have 10 plus 10 plus 5, so we're going to end up with 25. One last question before we finish off this lesson is I just wanted to practice with you some of the kinematic equations. Let's just do a football style question, because if you can do the 2-dimensional stuff, you can definitely do the 1-dimensional stuff. Let's do a problem where we're going to do a field kick. We have a football on the ground, we go launch the football, we go all the way up, coming back downwards. We're going to send this football up. Let's send it at 35 meters per second, and let's launch it at an angle of, say, 60 degrees. I'm going to ask you 2 parts of the motion. First part of the motion is the max height. So how high off the ground, what's the time it takes to get there. Second part of the motion, I'm going to ignore the max height. I'm going to go straight to the total hang time. The hang time is the total time it spends in the air, which is the start when I kick it, and the final when I hit the ball. Because this is a two-dimensional problem, we're going to separate our columns. Here's our x column, here's our y column. For the first part of the motion, because we're dealing with max height, it's important to use my down. We're going to take this velocity. Unfortunately, because this is a diagonal, we need to break this down to the x part and the y part. The x part in this case here is the adjacent side. So if I want to do the initial velocity, earlier I put vi, but you can also put vo, that not symbol there means initial. If we go 35 cosine of 60, that's going to give you 35 to 60. When I launch this football, I'm actually kicking it forwards at 17.5. Going in the upward direction, we have our v naught, but that's in the y column this time. This time it's going to be 35 sine 60. So 35 sine 60 gives me 30.3. Both of those can be positive because I'm launching it forwards and launching it upwards. Acceleration-wise, like we mentioned before, the acceleration horizontal is 0. Once the football leaves my foot, I can't influence it anymore. Whatever speed it has, in this case here 17.5, it's just constantly going to be 17.5 going forwards, similarly at the max height position. For acceleration due to gravity, however, it is going to be negative 9.8, so it opens down towards the ground. The one other value that we have with the max height question is, in the vertical direction, I know all objects that go upwards have to slow down, By the time it gets to the max height, we actually know that the final velocity in the y direction actually is 0. So we're going to actually use that to our advantage here. Let's say we want to calculate the distance from the max height. I go straight to this formula here, say v squared is equal to v naught squared. You'll notice that I'm under the y column here, so that means I'm only going to be using these y values. Make sure not to cross these two. We're going to take the final velocity at max height. I'm not going up with the 0 squared. Initially, when I took the football up at a diagonal, it only went 30.3 upwards, 2 times the acceleration of negative 9.8, and that'll give you a max height. So I'm going to punch our way through the problem here. I'm going to be off by a little bit of rounding. 30.3 squared is going to be 918.89, negative 19.6b. I'm going to bring the 19.6b over to the left side. If you can, keep all the decimals in your calculator. Use the answer button to recall down things unrounded. Take that number divided by 19.6, and what I'm getting is 46.8 meters. From the point that it was launched to the very top, we're now 46.8 higher than what we started. I could similarly, once you know the displacement, you can calculate time and whatnot, and we'll demonstrate for you the time for part B of the question. Say we have calculate the hang time. What's the total time this thing here is in flight? Based on the symmetry of the problem, it is going to be half the time up and half the time down. The nice thing about this football question, because when I put my blindfold on, the football was on the ground. I don't actually know it went upwards. When I take my blindfold off, it is still back on the ground. For the total hang time part of the question, especially again in the y direction, the displacement is actually zero. So, part B of the question here, let's just trace down some of the numbers. The horizontal velocity was 11.5. The initial velocity in the y direction was 30.3. Acceleration doesn't change over the entire course of the motion, negative 9.8. But this time, because the football again started on the ground, ended on the ground, the total displacement between start and finish is 50. Depending on which column that you know more, in both of these problems I knew more on the y side, that gives me a hint. I'm going to do my kinematic formulas on the y side first. We're going to try to find time first in all of these questions, because once you find time, time is a scalar. Time can actually jump back and forth between the two different columns. So I'm going to just punch our way through the values here. The displacement, I'm no higher or lower than where I started. Initially, I was picked upwards at 30.3. Time I don't know yet, plus 1/2 and negative 9.8 times d squared. 0 is equal to 30.32 minus 4.92 squared. In the cannonball type question, this one here would end up as a quadratic formula. Nicely in this case here, because our displacement was 0, we can just simply use a factoring technique. Let's pull our t term out of this binomial. We have 30.3 minus 4.92. When we have two numbers multiplied to give 0, either the first number has to be 0, that's when the football was already on the ground, or this whole binomial, this 30.3 minus 4.92, that together has to be 0. We solve that through there, and we get our time of do one last problem here is calculating the final velocity. So this football here had been launched upwards, had been launched downwards. We now figured out at this point, we're 6.2 seconds since our launch. Notice that no matter how steep this football here looks like it's falling downwards, this velocity is going to be a two-dimensional velocity, meaning I need to know how much is it going forwards and how much is it going downwards. The x part is easy. Because in the x part there was no acceleration, once the football leaves my foot, I can't influence anymore. This 17.5 will stay constant at 17.5. So at first when I launched it, forward 17.5. A little bit later, 17.5. A little bit later, 17.5. Even by this ending position, it's still going to be 17.5. The one that we do need to calculate, again, is in the y direction. If you give gravity 6.2 seconds, and I had launched it upwards at a 30.3, what would be the final velocity? So v is equal to v naught plus at. What is the final velocity having launched it upwards? 30.3. Acceleration 99.8. Multiplied by 6.2 as your time. Punch it through there, 30.3. Again, I'm going to be off by a little bit of rounding. Just want to keep your answers to two or three Phys. Again, based on the symmetry of the problem, you'll see, oh, when I was going upwards, positive 30.3. When I'm on the other side of the parabola, I'm actually just traveling negative 30.3. And similarly, if you did an actual Pythagoras and actually found this, you actually will figure out your velocity was your launching velocity at the beginning. You can do the square root of 17.5 squared, add it to 30.3 squared. Again, you'll notice that I dropped the negative there. The negative just meant downwards. I already showed you that negative direction. This one here, everything goes to 10, 20.5 squared plus 30.3 squared. Give or take a little bit of rounding, but this is 35 meters per second. That's the magnitude. But being a vector, again, I need the direction. Based on the symmetry, I would assume that this theta is the thing that I launched at earlier. Let's just verify that theta is the inverse tan. Again, I'm just going to take the positive value opposite this 30.3. divided by my 17.5 gives you an inverse question. So inverse tan, make sure you're in degree note, 30.3 divided by 17.5. This gives me 6 meters. One last comment here is this is not going to be self-reduced like the earlier question. Because this one here is a side view problem, what we're going to do is we're going to decide the x is called the horizontal. That's the pure direction, that's going to be the second direction. And we're going to aim such and such degrees lower or below the horizontal. So 60 degrees below the horizontal, which matches perfectly. If you look back at the start of the question, we actually had launched it upwards, the same 35 meters per second, but above the horizontal. Feel free to drop any questions in the comment section or on that general forums tab. Well, that'll be your lesson for today. We'll review through forces in the second lesson. Thanks, guys.